Thank you for having me. Eric just laid out the vision for what we need to do with nanoscale technology, and I'm in a slight departure from the rest of these talks. I'm going to talk a little bit about the practicalities of actually doing something. So I want to talk a little bit about who I am. My name is HP van Braam. I'm a board member of the Godot Foundation, which is an open source game engine that will become relevant in a moment. Founder of Prehensile Tales, which is my Godot consulting for a company, and Eric approached me to help him build out this vision for a molecular design tool. I'm a contributor to the game engine and a free and open source software evangelist, and I'm not terribly great at selling myself, so I'm just going to go move to the next share. So what is the goals for MSAP1? We want easy-to-use, powerful molecular editing tools that someone can install on their computer and actually use. People should think of this more like installing a 3D content editor like Blender or Maya than trying to install some like science tool for the regular user. We want real-time feedback. We don't want people installing this tool or even users installing this tool and having to wait like hours, days in some cases for the simulation to run or to get any feedback from what they've just done. We want it to be open source, and because a tool of this importance, I think, if you lock it behind a paywall for everyone, then this technology is not going to go anywhere, right? Imagine if you only had access to a word processor, if you were able to spend like $30,000, $40,000 a year on it. Nobody would be using word processors, and nobody, like, who would even be writing books, right? Well, pen and paper, maybe. I forgot about that, weirdly enough. We want it to be accessible for novices. Like, as Eric pointed out, there is a disconnect between the amount of effort being put into this and the amount of effort being put in designing tools. And I think a large part of this is because there is no way to envision what we need to build. So we need non-experts to build these tools. But on the other side, we also need powerful tools for experts to actually use these tools today. So the first part of the problem is, like, how do we even like get this stuff on the screen? We see a lot of tools that can maybe display like 100,000 atoms, but these systems will be much more complex than that. It turns out that rendering a lot of geometry on the screen is a very solved problem. The fact that not all science tools are able to display more than 100,000 atoms is kind of strange. Because this screenshot, it looks really great. It's actually from a 7-year-old game already, right? So this is not recently solved. So how we solve this problem is by using a game engine. In this case, the Godot game engine, which is also open source, which means it doesn't drag on the ability for us to distribute this tool. So third most used game engine overall, MIT licensed. The built-in programming language is already Python-like, and as most scientists use Python or Python-like tools, it is actually fairly easy to get into. And most importantly, it has a very good built-in UI toolkit, meaning that we can build user interfaces that are actually usable without you having to be an expert in how to do that. So another important thing here is design, right? As we said, we want this to be accessible to novices. And the fact of the matter is programmers are not designers, scientists are not designers, but designers are designers, right? And the thing here below here is, for instance, the user interface to my last program that I developed, right? This is not something that a regular user is going to want to use. So to this end, we have the following generalized layout of the program, which is designed to be inviting, designed to be easy to use, and useful for novices, as I pointed out before. So why does it even matter, right? Because we're talking about these lofty goals, these high-level things. Why am I talking about design? And it's because if you build a tool that can do everything, but nobody can figure out how to do it, then the tool is not very useful. Right? So, but it also helps power users, because if you have a well-designed tool, then you can intuit how to do things that you've not done before without having to like read a manual to do it, right? Also, it's just nice to have a tool that looks nice, right? So, but it's not just about visuals. APIs are important. If you want to have a tool that you can integrate in a workflow, then you have to think about what kind of workflows there are and how to integrate with them. That also means performance, right? If you design a program to be fast, then it is nicer to use, right? But it also comes down to things like, how do you do an undo-redo system, which is extremely boring things, and not someone who is trying to like revolutionize the world of fabrication is going to want to think about maybe. But if you actually want to revolutionize the way that manufacturing is done, you need to have like the simple thing like being able to copy-paste something between programs. You need to be able to like undo something you did before without losing all of your work. I will try to go a little bit faster. Let's see. Scientifically, we're using open source scientific libraries to actually like do scientifically accurate modeling and prediction. Today, we actually have a robust molecular editor, an easy-to-use interface. We can attach motors, which are kind of magical devices at this point, but we can use them to simulate designs. You have fast integration with OpenMM and OpenFF, fast rendering of large number of items, video rendering. Very quickly, I want to show one video. Then, so for anyone in this field, you might have seen this image before. I took this from the internet on purpose so that it might be an image that you've already seen. And these days, we can do this. We've cut away part of the thing and actually do real-time a simulation of this thing with scientific accuracy. This is the pump actually moving some atoms, and the same thing goes for here. This is the planetary gear, which is also a fairly old design, but you can see here actually being simulated and doing the thing that we set out to do. This is a design from, when did you do this?
Was done in the early 90s. It was refined a few years later.
Right, so this is like an old design that we can now actually validate that it works, and in a reasonable timescale. Like this simulation ran on an M2 MacBook that you can just own, right? So what we need, what we do want to do immediately, improve the catalog design tools, adding support for sharing research and designs within the tool, and making it easy for third parties to create Python plugins. What we need input from users, particularly around our protein workflow, because we haven't really nailed that down. Alpha users willing to give us bug reports and do iterative testing. That is, take some time out of your day that after you've put a bug report, we fixed something, actually validated it, we fixed it. And as Eric pointed out, funding would be very important, obviously. That's the end. How did I do time-wise? Yeah, we're going to do a launch event like soon, and then this will all be like easily available to everyone. Yeah.
I'm curious what type of physics is in it now, and what type of interactions are you built in? How are interactions?
So we're using OpenMM dynamics with which force field? The Emperor?
The short answer is it's a molecular dynamics system. The force field is the standard one that's used in computational chemistry modeling.
Yeah, we don't have like QM or anything right now.
It's a very good model for this purpose.
Awesome.
Thank you.